Welcome to the deep dive. We are really thrilled to have you here with us today.
Yeah, glad you could join us.
If you're tuning in, you're probably the kind of person who loves to stay ahead of the curve, gaining thorough knowledge quickly, but without that dreadful feeling of information overload.
Right. Nobody wants to get bogged down in jargon that doesn't actually explain anything.
Exactly. We know your time is valuable, so we have curated something truly mind-bending for you today.
Today, we're looking at some foundational state-of-the-art material in generative AI.
The heavy hitters.
Yeah, specifically, we're diving into excerpts from the foundations of the generative intelligence state-of-the-art and a brand new, really heavyweight research paper.
What's the title on that one?
It's titled Rethinking the Value of Multi-Agent Workflow, a Strong Single-Agent Baseline.
And when we say heavyweight, I mean, we really mean it. This research is a massive collaboration. You've got minds from UT Austin, Amazon, Emory, Northeastern, and Georgia Tech, all on this.
It is a serious lineup.
It really is. And our mission for this deep dive is to explore a massive plot twist in the world of artificial intelligence.
A huge pivot from what everyone thought was the standard.
Right, because right now there's a huge trend in tech where developers are building these massive, complex teams of AI agents to solve problems. It's being sold as the ultimate future of computing.
But this paper suggests that this multi-agent approach might actually be, well, an expensive illusion.
An illusion. And we are going to examine how a single, well-structured AI can do the exact same job faster and incredibly much cheaper. Okay, let's unpack this.
To really appreciate the twist here, we first need to define the baseline of what is happening in the industry right now.
Setting the stage.
Yeah. We are currently living through the absolute peak hype of large language model multi-agent systems.
MAS for short.
Right, MAS. And the standard thinking driving billions of dollars in investment goes like this. If you have a complex task, you don't just ask one AI to do it, you build a team.
You specialize.
Exactly. You have multiple AI agents collaborating. Each one is assigned a distinct role, provided with specific tools, and governed by strict communication patterns. You are essentially building an assembly line of artificial intelligence.
Let's ground this in reality for a second. The paper uses a very specific, real-world example that I think everyone listening has experienced at some point.
The shopping one, yeah.
Yeah, imagine you are building a session-based query recommendation system for an e-commerce site.
Basically, the system that tries to guess what you're actually looking for when you're frantically searching on your phone.
And making typos.
So many typos.
Let's walk through the scenario. You, the customer, are typing fast, and you accidentally type the search string, crinoline underskirt women's.
Obviously, crinoline isn't a word.
No, it's not.
Mm-hmm.
You hit search, you see some weird results, and then you click on two different products that both happen to have the correctly spelled word crinoline in the title.
Think about what happens behind the scenes in a standard multi-agent system to handle that typo and those subsequent clicks.
The whole process.
It passes your session through a literal flowchart of mini AIs. First, a session analyzer agent looks at your initial weird search.
It takes notes.
Right. It packages up its notes and passes them over to a language normalizer agent. And its only job is to clean up text.
Just a spell checker on steroids.
Basically. Then that output goes to an intent detector agent to figure out what you actually want to buy. Next, an ensemble agent takes all of this and uses a chain of thought reasoning process to generate a corrected search term.
And it might even loop back on itself, right? Arguing with previous agents if it isn't confident.
Exactly. And finally, a final output formatter agent takes the winning result and spits out the cleanly formatted corrected search term, crinoline underskirt women's.
It sounds incredibly sophisticated. You picture this bustling digital office inside the server with all these specialist robots passing manila folders back and forth to give you the perfect search result.
And developers love building these flowcharts.
Oh, they love it. But this is where the paper pulls back the curtain on the whole operation.
What's fascinating here is that almost all of these multi-agent systems are actually entirely homogeneous.
Homogeneous meaning they are all exactly the same underneath.
Precisely. The industry has been touting these complex teams of agents, but the paper points out that they are all just the exact same underlying base model.
So there isn't actually a team of different specialists.
No. A developer might be using GPT-4 Mini or Claude 3.5 Haiku for the entire system. That means the session analyzer, the language normalizer, the intent detector, they're all just that identical base model wearing different hats.
Just putting on a different name tag.
Right. They're given different system prompts to act like specialists, they're handed different API tools, and they sit at different positions in the workflow, but they share the exact same neural network brain.
It's like Eddie Murphy playing every single character in The Nutty Professor.
That is a perfect way to look at it.
You think you're watching a dinner party with 6 different people having a debate, but it's literally just one incredibly versatile actor running around changing costumes.
Which is funny, but computationally, it's a huge deal.
Which leads us to the central hypothesis of this entire paper. If all these specialized agents share the exact same underlying brain, can't one single agent just role-play the whole workflow through a structured, multi-turn conversation with itself?
Why do we need the complex, disconnected assembly line handing files back and forth at all?
Right. So did they test this?
They didn't just ask the question theoretically, they rigorously tested it across 7 different highly complex benchmarks.
Heavy-duty stuff.
We are talking coding tasks like human evil, where the AI has to write functional Python from scratch, mathematics like GSM-8K, which involves tricky grade school logic puzzles.
General question answering too, right?
Yeah, domain-specific reasoning, real-world planning. And the verdict is a resounding yes. A single agent using multi-turn conversations can absolutely simulate these highly tailored multi-agent workflows.
And how did it perform?
It achieves comparable performance across the board. And crucially, it drastically reduces the computational costs.
Here's where it gets really interesting. How does simulating a conversation with yourself suddenly make everything cheaper?
It comes down to memory.
Right. It's all about a piece of technical magic called the KV cache, or key value cache. If you were going to take away one technical concept from this deep dive today to sound incredibly smart in your next meeting, make it this one.
The KV cache is fundamental to how modern transformer models function.
Break that down for us.
Okay. When an AI processes text, it computes attention states for the tokens, the words or word fragments it has seen so far. The KV cache stores these computed key and value matrices.
So it remembers the math it just did.
Exactly. Without this cache, the model would have to redundantly recompute these attention states for all previous tokens every single time it generates a new token.
That sounds intensive.
In computer science, we call this quadratic computational complexity. As the context gets longer, the computation required doesn't just go up linearly, it skyrockets, making it highly inefficient and very expensive.
Wait, quadratic computational complexity? You're losing me a bit. Is it kind of like reading a dense textbook, but every time you flip the page, you have to start reading again from chapter 1?
That is actually spot on. To understand page 50, the AI is literally forced to reread pages 1 through 49.
Wow.
That's what we call pre-fill costs in the industry. Think about that multi-agent assembly line we discussed earlier.
The shopping search one.
Right. Every single time the language normalizer passes its information over to the intent detector is a fresh instance. It has no memory.
The blank slate.
It has to process the entire history of the task from scratch. It has to read from chapter 1 just to understand what it's supposed to be doing.
So every handoff is basically a massive tax.
That creates massive, overlapping, expensive pre-fill costs at every single node in the flowchart.
So using that book analogy, the KV cache is like having a perfect photographic memory of everything you just read. When you turn to page 50, you only have to process the new words on that new page. You don't have to start from chapter 1.
Yes, and that is exactly where the single agent approach completely changes the game.
Because it's just one conversation.
Because a single agent keeps the entire conversation history in one continuous thread. It reuses the KV cache. It retains the context across all the different roles it is playing.
It just remembers what it just said.
The researchers proved that for homogeneous workflows where there is massive contextual overlap between all the different agent interactions, executing it as a single multi-turn conversation is asymptotically no worse in performance.
And cheaper.
Almost always significantly cheaper. You completely bypass that massive computational cost of starting fresh for every single agent handoff. The single model just remembers what it did in its previous persona.
So what does this all mean? We know the multi-agent illusion is often just one model in different hats, and we know the KV cache makes keeping it all in one single conversational thread drastically cheaper.
But the tricky part is building it.
Right, because developers spend months manually tuning these multi-agent flowcharts. We need a way to build the single-agent equivalent without losing the magic.
This brings us to the fascinating solution the researchers built. They call it OneFlow.
OneFlow, what does it actually do?
OneFlow is a brilliant algorithm designed to automatically generate multi-agent workflows that are specifically tailored to be executed by a single agent.
Automatically.
Right. Instead of a human developer guessing how to structure the AI's internal monologue, OneFlow automates it. To find the optimal workflow for a specific task, it uses a technique called Monte Carlo Tree Search.
Okay, Monte Carlo Tree Search. That sounds like a casino game. Can we break that down?
Think of it like an AI trying to solve a massive maze. Instead of just walking in and hoping for the best, it simulates thousands of different paths simultaneously.
Branching out everywhere.
It explores a massive tree of possible workflows, running up to 20 optimization iterations. It tries one path, say, having the AI double-check its work before answering, and evaluates the result.
And if it works,
If it's good, it explores further down that path. If it's bad, it cuts it off. It's systematically hunting for the perfect balance between high accuracy and low computational cost.
and the engine running this massive search is what really caught my eye in the paper. They use a dual-meta-LLM architecture. I like to think of it as a two-headed design team.
That's a great way to put it.
Head number one is what they call the creative designer. This LLM acts like the wild, disruptive creative director at an ad agency.
The creative designer's entire job is to look at the error logs from previous workflow attempts in the maze and throw wild ideas at the wall to boost performance.
Just throw everything at the wall.
It might suggest adding a complex chain of thought process or an ensemble voting system where the agent debates itself 3 times. It is entirely focused on pushing the boundaries of accuracy, regardless of the price tag.
But as anyone who has worked with a wildly creative director knows, if left to their own devices, they will blow the entire budget on day one. A workflow that is perfectly accurate but requires the AI to loop 50 times is too expensive to run in the real world. And that is why we have head number 2, the critical reviewer.
The critical reviewer acts as the strict editor, or the ruthless accountant of the operation.
The reality check.
It takes the designer's proposed code, reviews the hard cost metrics of the top solutions found during the tree search, and aggressively trims the fat.
So it cuts down on the loops.
It might look at a 5-step verification loop the designer built and realize it can achieve 99% of the same accuracy with just a single, well-crafted verification step. It makes the workflow cost-efficient without losing the accuracy gains the designer achieved.
The collaboration between these two meta-LLMs is what makes OneFlow so effective. You get the unbridled problem-solving of the designer, tempered by the real-world constraints of the reviewer.
And the hard data from the source material absolutely backs this up.
Let's get into the numbers.
The researchers benchmarked OneFlow across all those domains we mentioned earlier. Let's talk about what that actually looks like in practice. Take human evil, for instance.
The coding benchmark.
Human evil is the gold standard for testing an AI's coding ability. It presents the model with a Python function signature and a doc string, and the AI has to write the rest of the code so it passes hidden unit tests.
Pass or fail.
It's unforgiving. A single syntax error means failure. The workflows designed by OneFlow executed entirely as a single agent, having a structured internal monologue matched or beat the traditional manually designed multi-agent setups.
And those setups took developers weeks to hand code, right? Separate coder and tester agents.
Exactly. And it matched or beat them.
It did the same thing on GSM-8K, the grade school math benchmark that famously trips up LLMs with confusing logic puzzles.
Yes, and it conquered Hotpot QA, which tests complex general knowledge.
In Travel Planner, which tests an AI's ability to use tools to book flights and hotels. But I really want to focus on the shopping MMLU benchmark, because if you are listening to this and you work in business or software development, this is the metric that will drop your jaw.
Shopping MMLU is a highly specialized e-commerce benchmark. It deals with incredibly complex tasks like multilingual query understanding.
Figuring out what a customer means when they search in a mix of English and Spanish. Right?
Yeah, an aspect-based sentiment classification, determining if a review is praising the battery life but complaining about the screen. OneFlow achieved state-of-the-art performance on 9 out of 10 of these shopping tasks.
And the cost reduction here is the true mic drop. Let's frame this for you, the listener. If you are a developer or a product manager running 1 million of these shopping queries a day, inference cost is everything.
It is the entire ballgame.
It's the difference between a profitable feature and a server bill that bankrupts your startup. On tasks like product selection, the traditional multi-agent system, a highly respected framework called Flow, cost $1.47 per inference.
$1.47.
When the researchers swapped to OneFlow executed as a single agent, that cost plummeted to just 26 cents.
From $1.47 down to 26 cents, that is an almost 85% reduction in compute cost.
It's staggering.
And the critical detail is that it didn't just maintain the performance. The accuracy actually went up from a score of 0.638 to 0.678.
So you get better answers.
You are getting a measurably smarter system for a fraction of the price, entirely because you are leveraging that shared KV cache in a single continuous conversation instead of starting from chapter 1 over and over again.
That is the holy grail of software development: faster, cheaper, and better. It completely upends the narrative that more agents equal a better system.
But of course, we have to look at the whole picture.
Right, no technology is a silver bullet that solves every single problem. There are distinct limitations to this single-agent approach.
If we connect this to the bigger picture, we have to look at where the single-agent paradigm hits a hard physical wall. The paper explicitly states that single LLM methods cannot capture truly heterogeneous workflows.
Let's define that clearly. We spent the whole deep dive talking about homogeneous workflows.
Yeah.
The single actor playing all the parts because they share the exact same underlying base model.
Right.
A truly heterogeneous workflow is when a system uses completely different base models simultaneously.
Imagine a scenario where you are processing millions of medical records. You might pair a very fast, very cheap model, like GPT-4 Mini, to handle the simple task of extracting dates and patient names.
The busy work.
But for the complex task of actually diagnosing the symptoms in the notes, you hand the data over to a highly complex, heavier model like Claude 4.0 Sonnet to do the deep analytical heavy lifting.
In that scenario, you are assembling an actual team of diverse specialists, not just clones wearing different hats. You are hiring a speedy intern for data entry and an expensive senior doctor for the analysis.
But here is the catch, and it goes right back to the server-level reality of that secret sauce we discussed earlier.
The KV cache.
The coordination cost. Because these heterogeneous models have entirely different underlying architectures, they have different neural network weights, different parameter counts, different tokenizers, they absolutely cannot share a KV cache.
They speak different languages entirely.
They might literally live on entirely different server racks in different data centers.
Going back to our book analogy, you can't share a photographic memory if you don't share the same brain. When the cheap, fast model finishes extracting the dates, it has to serialize that data, send it over a network, and the expensive heavy model has to receive it, tokenize it from scratch, and process it from zero.
With a heterogeneous team, you are forced right back into the expensive reality of reading the book from chapter 1 every single time you pass information between the different models.
The prefill tax is back.
Which means the open frontier for AI research right now is figuring out how to balance this equation. How do we build heterogeneous systems where the unique strengths of mixing diverse models actually outweigh those massive coordination and prefill costs?
Did the researchers look into that at all?
The pilot study in this paper showed something very revealing. Right now, a highly optimized single-agent baseline, like the ones built by OneFlow, can actually match the performance of automatically discovered heterogeneous workflows.
Really? Even against the mixed teams?
Simply because the heterogeneous systems are still so clunky and expensive to coordinate, the intern and the doctor spend more time trying to understand each other's handwriting than they do actually solving the medical case.
Wow. That's a great analogy.
This raises an important question. How do we summarize this incredible journey we've just been on, and what should our listeners take away from it?
I think the summary is a massive reality check for the industry. For now, if you are building an AI system or paying for one, and it uses the exact same underlying model for every step, splitting it into multiple disconnected agents is often just an expensive illusion.
A very expensive one.
A single agent, properly structured to utilize its KV cache through a tool like OneFlow, is the gold standard baseline. It is going to save you compute, it is going to save you a massive amount of money, and as the shopping MMLU benchmark showed, it will likely perform even better.
It is vital to remember why this matters outside of the academic research lab. Whether you are prepping for a tech meeting, managing software budgets for a massive enterprise, or you are just insanely curious about how the AI tools you use every day actually work under the hood, this is a highly practical mental model.
It applies everywhere.
Efficiency often beats complexity. Throwing more agents at a problem isn't always the answer if those agents aren't sharing context efficiently. It's about working smarter, leveraging memory, and avoiding redundant work.
Efficiency over complexity. I love that. Which brings me to a final thought I want to leave you with today. Something to mull over as you go about your day.
Always good to end on a big idea.
We've just learned that a single AI can perfectly simulate an entire collaborative team simply by having a highly structured, multi-turn conversation with itself. It role-plays the analyst, the reviewer, the editor, all in one continuous flow of memory without ever dropping the context.
It's a fascinating capability of the technology that we are just beginning to harness.
But think about what that means for how we structure our own human workflows. We spend so much time in endless meetings, handing off tasks to different departments, losing context at every step.
Passing the manila folders.
Essentially, forcing our colleagues to reread the book from chapter 1 every time we send an email. If an AI achieves its absolute highest efficiency by internalizing the team and carrying the context perfectly from step to step, could the ultimate key to our own complex problem-solving simply be learning how to ask ourselves the right questions from different perspectives in the right order?
A profound thought to end on.
Thanks for joining us on this deep dive. Keep asking those questions, keep learning, and we will catch you next time.